Good morning, everyone. On behalf of the Geological Society of Sri Lanka, I am delighted to welcome you to this insightful public lecture on spatial data science for natural resource management. We are honored to have with us today Dr. Indishe Senanayake, a research associate from the University of Newcastle, Australia, who will share his valuable expertise on this timely, valuable, and important topic. Before we begin, I would like to acknowledge and thank you all for joining us today and extend a warm welcome to our esteemed guest. This lecture is a part of GSSL's ongoing effort to promote knowledge exchange and engage with cutting-edge research that can have a practical impacts on Sri Lanka's natural resource management. To formally introduce our speaker today, I now invite Professor Amila Ratnayake, the president of GSSL, to read the citation of Dr. Indishe Senanayake. Please join me in welcoming Professor Amila Ratnayake.
Good morning, ladies and gentlemen. It's my great pleasure and honor to be here as the president of the Geological Society of Sri Lanka in this GSSL public lecture series. The title of the today topic is Spatial Data Science for Natural Resource Management. Without taking much time, now it's my privilege to introduce our distinguished speaker, Dr. Indishe Senanayake is an accomplished researcher with over 60 scientific publications, including high-impact journal articles, technical reports, and conference papers, primarily focused on the spatial data application. He earned his BSc in Engineering Honors and MPhils from the University of Moratuwa, Sri Lanka, where he also served as a senior lecturer before pursuing his PhD in Environmental Engineering at the University of Newcastle, Australia. His PhD research focused on enhancing the spatial resolution of satellite-based soil moisture products. Currently, Dr. Senanayake works as a research associate at both the School of Engineering and the School of Environmental and Life Sciences at the University of Newcastle, Australia. In addition, he teaches spatial data science modules to the undergraduate students. His research encompasses a wide range of spatial data science applications, including soil moisture, vegetation, surface hydrology, wetland, ecology, mineral exploration, mining rehabilitation, and agriculture. He has presented his work at the numerous national and international conferences and has worked as a reviewer for a number of international journals. Dr. Senanayake's research addresses real-world changes in hydrology, ecology, soil science, and the land surface dynamics. Through integrated, data-driven spatial approaches, his work contributes to a deeper understanding of the environmental process and support sustainable resource management. Now, I would like to warmly welcome Dr. Indishe Senanayake, and it's over to you, sir.
Can you hear me clearly?
Yes, sir.
Yeah, great. Good morning. Thanks for the nice introduction. And thanks to the GSSL for inviting me to deliver this public lecture. I truly consider this as a great honor. I'll share my screen. Can you see my screen now?
Yes, sir, we can see it clearly.
Right. So today I wish to talk about how spatial data science can help managing natural resources. Primarily, I'll be talking on landscape and soil management in post-mining rehabilitation. I'd like to divide this talk into two main parts. First, I'll talk about one application of spatial data science, landform evolution models. I kept this topic of this talk a bit open, but thought landform evolution models would be a better topic for the audience here. This involves managing soils, vegetation, landscapes, and mine rehabilitation. When it comes to natural resource management, so this is really important topic. I hope you don't mind if I focus mainly on this topic rather than talking broadly about natural resource management. And secondly, I'd like to talk briefly about a few challenges and opportunities we are having with regard to spatial data science, especially in Sri Lanka. Finally, we can have a question and answer session. First, let's see what's spatial data. In simple terms, spatial data has location values. If you take your bank account, for example, its daily transactions are data, but these numbers generally don't have any location value. Then look at a series of boreholes, which you drill for an exploration. Each of these boreholes can be tagged with their location, with X and Y coordinates, or latitude and longitude. They all have location values, which makes them spatial data. Boreholes are generally points in space, but look at a river, for example. It has location values along its path, which can be a line instead of points in like boreholes. But still these lines have location values. If you take population of each ground military division in Colombo, those ground military divisions have location values because they are located in space. But now they are not points or lines, but polygons. We call this type of data as spatial data, geospatial data, GIS data, geotag data, or georeference data. These terms might have slight differences, but they all have a common attribute, the location values. As most of you know, they can be vector data, points, lines, and polygons, or raster data, or grid with pixels, triangular, irregular networks, etc. You can get them by field surveys, satellite imagery, airborne data, all maps, tables, and so on. But the beauty of this spatial data is we can overlay data of same location based on their georeferencing. Those data sets might be taken at different times, representing different attributes and having different spatial resolutions, yet we can overlay them on a GIS platform because they are geotag data, georeference data. Most of natural resources, vegetation, forest, mineral deposits, water bodies, and landscapes have location values, so they all can be represented as spatial data sets. And they're interrelated with many other factors. For example, vegetation growth is related to soil quality, soil moisture, solar radiation, irrigation, all of which are spatial attributes. So once we analyze them together on a spatial data analysis platform, we can come up with some useful answers for the real world problems. I've used my spatial data skills for projects in a wide range of areas, mainly in natural resource management, in areas such as hydrology, vegetation, soils, agriculture, and publish our findings in a number of international high-impact journals. Initially, I was planning to talk about 4 applications, but that'll be too much, and this lecture will be too long. So finally, I decided to talk about only one application, landform evolution models. Landform evolution modeling was first developed in 1970s with the advancement of computer technologies. Initially, they were used to understand landscape evolution at geological timescales. You know what geological timescales are, like quite long. But from 1990s, they have been used in mining industry to see how the mining landscape will evolve with time to examine whether they are erosionally stable over a long period of time. Especially, this plays an important role in forecasting the erosional stability of post-closure mine rehabilitation. The University of Newcastle, which I'm working in, is located in the Hunter region of New South Wales. It's the Hunter River catchment, which is about 21,000 square meters in size. That's about 1/3 of Sri Lanka, right? Hunter region is known for coal mining. There are many mines which are closed, and also we have several active open pit coal mines in the Hunter. When coal is mined, the waste material, it can be overburden, tailings, gang material. They are piled somewhere close to the mine. So the mines are huge and deep compared to most of the mines in Sri Lanka. If you go to such mine site, you'll be amazed with what we humans can do, like that massive. Look at these photos. These are such post-mining waste files. These piles often look like small mountains or mountain ranges. But this has to be done systematically with proper slope angles and design. So that the idea is these waste piles should be blended with surrounding natural landscape with the time. So these hills you see in this slide are not natural hills, natural mountains, but these are such mine waste piles blended with the surroundings, having native vegetation, native pasture on it. You don't even know they are man-made mine waste piles if you're passing by, because they look like natural real mountains. But one of the problems with these post-mining landscapes is soil erosion. Obviously, there can be erosion on any slope, even on a natural slope, but these post-mining hill slopes can have quite high erosion rates due to soil characteristics, salinity, lack of vegetation, and improper design, improper slope angles, improper shape. The other problem, again related to erosion, is the formation of rilling and gullies. Rills are shallower compared to gullies. Gullies are generally deeper than 30 centimeters. Even on natural environments, on analog sites, you see rills and gullies. But the question is, on post-mining landscapes, do we have more gullies compared to the natural environment? Are those gullies acceptable compared to the surrounding natural environments? Is the erosion rates acceptable compared to the surrounding natural untouched environments, landscapes? Look at these photos. This one here, I took this at a mine site recently. You can see small rills, gullies in this area. There's no big impact with these gullies at the moment, but you can clearly see the gullies formed here. This one here is a gully head. It's not from a mine, but from an analog site, which had less human interactions. We checked the historical air photos of the area of this analog site. This gully can be seen even in 1950s. So that's about more than 70 years. So gullies are always there in natural environment. Again, the question is, are we having more erosion and more gullies in mine waste landforms? So long-term stability is a major concern in the rehabilitation and closure of mine waste landforms. And authorities state that waste rock landforms should be designed to ensure that the final landform is safe, stable, and not prone to significant erosion. According to a paper by McKenna and Van Zyl in 2020, tailing dams should have 1,000-year design life upon mine closure. So usually less than 10 tons per hectare per year is considered as stable, the erosion rate, 10 tons per hectare per year. but this can go to around 40 tons per hectare per year. In Queensland state, they made it mandatory to evaluate the soil erosion using landform evolution models for the post-mining landscapes. But in most cases, it is unclear how this waste material will weather form soils and their soil characteristics. These constructed landscapes often consist of steeper slopes and coarse textured material. They have low water holding capacity, less nutrients required for vegetation growth. In some cases, this material can be chemically hostile, having high content of salt, sulfides. So these landscapes are prone to erosion and subsequent formation of gullies. When the slope angles and or the topsoil are not suitable, that can be the major issue. There are several knowledge gaps, such as erosional stability, response to climate and extreme weather conditions, design suitability, and construction reliability to see how these structures will perform and blend with the surrounding landscape. So we need robust design evaluation process to examine this. Erosion pins. So if you look at this picture here, this is an erosion pin. These erosion pins are not that practical in these scenarios because we need forecasting for hundreds and thousands of years, or to know what will happen at the design stage before making those piles, rather than just measuring the erosion with an erosion pin. That's why we need landform evolution models to forecast the long-term performance of this final landform. So the insights obtained from using models can be applied to refine the landform design before construction. That will help to implement additional stabilization measures on the constructed landforms to prevent or minimize long-term erosion risk and formation of rills and gullies. So now we know that it's important to examine how landform will process over an extended period of time, hundreds of tens, thousands of years, with respect to erosion. In light of this, numerous soil erosion models have been developed. To name a few: the Universal Soil Loss Equation, USL, Mussel, Russell-Webb, have been developed to model soil erosion. Each of these models have their own pros and cons. These models were tested over different landscapes, and they showed different accuracy levels. Proper calibration is the most important thing with these models. So it's just not running the model, but it's really important to calibrate the models properly. Although these models, these USL, Mussel, Russell-Webb, are highly reliable and effective when properly calibrated and applied, they only predict erosion and overlook the deposition patterns. And we need the hill slope to be changed after one time step of the model, and then the modified or eroded hill slope to be subjected to modeling for the next time step. We don't need the initial landscape to be used at each time steps recursively. So that doesn't happen with these models, the USL, Mussel, Russell, and Webb. They don't dynamically adjust the hill slope elevation in response to the erosion and deposition. But with the advancement of computer technologies, people developed landform evolution models, LEMS, that use digital elevation models, we call DEMS, as you know, as input data. Gary Vilgus developed Siberia model, Tom Coulthard, Caesar list flood model, Tucker child model, Miles D model, a SPAM model developed by Dimuth, one of our undergraduates from University of Moratua, and who did a PhD at University of Newcastle. These can be given as some examples. Unlike traditional models such as Russell and Webb, these models do not require manual calculation of slope length and angle because they perform based on grid operation using the digital elevation model. Tom's Caesar model operates at hourly intervals, so it's good for simulating erosion at the scale of individual storm events, like 100-year return period rainfall, what happened to the slope after such rainfall, how the slope will behave during such individual high rainfall event. In contrast, Gary's Siberia model, it operates at annual intervals, focusing on long-term processes such as slope evolution and catchment-wide erosion. Dimuth's SPAM model can simulate pedogenesis processes such as soil armoring and weathering. This is and this is a good textbook on landform evolution models written by late Professor Gary Vilgus, one of the leading names in this field, and was my PhD co-supervisor. Now let's move to the theory behind these models. So this is the basic sediment transport equation, which predicts both erosion and deposition. This is the base for most of erosion models, especially for Siberia model, which is used in mining industry in Australia. So here, the total sediment output is equal to the sum of fluvial transport term and the diffusive transport term. Fluvial transport refers to the movement of sediments by flowing water, typically rivers, streams, or runoff. It's driven by the energy of the flowing water. So this is the main contributor to the erosion. Diffusive transport, on the other hand, also known as hillslope transport or creep, refers to the gradual movement of sediment downslope due to the gravity. It's often a slower and more localized process compared to the fluvial transport. So here, if you look at this equation, diffusive transport is diffusivity, D, which is a parameter, multiplied by S, that's the slope in tan. Fluvial transport is beta 1, again a parameter, representing erodibility, Q, the discharge to the power M1, and tan slope, S to the power N1. N1, M1, beta 1, all these are parameters. So now we have to calculate beta 1, M1, N1, and D based on the individual site characteristics. They are not constant. For each site, these parameters change. So these are site-specific parameters, which include vegetation factor, soils characteristics, rainfall, etc. They are all hidden or embedded within these parameters. So DEMS, or digital elevation models, can be identified as the key input data set in many of these landform evolution models. So the simulations are performed as pixel-wise operation. I think you're familiar with raster calculations, raster processors, matrix calculations, so it's similar to that. So in other words, the erosion equation is linked together on a finite element grid. Obviously, it's a digital terrain model, or DTM, not the DEM or DEM, if you are very specific about the terms. But in the industry, people usually use the term DEM, although the term DEM might not be technically accurate. So I'll use the term DEM in this lecture, but you know what I mean is DTM, digital terrain model. Early days, we used 30-meter or 60-meter DEMs from SRTM or ASTER products. But today, we need much higher spatial resolution DEMs to capture the small gullies and rills. But now in Australia, we have a web portal called Elvis, where we can download 2-meter or 5-meter LiDAR-derived DEMs for most of the areas. Sometimes mining companies run their own airborne LiDAR surveys to create DEMs for continuous monitoring. So fine spatial resolution, for example, 10-centimeter DEMs with high terrain details are now achievable due to the recent advancements of LiDAR-based remote sensing technologies. So these days, we often work with high-resolution LiDAR DEMs having 10 to 30 centimeter resolution. So one might think it's easy to run a landform evolution model once you have a DEM. That's not correct. DEM alone is not enough. There are a lot of factors affecting erosion other than the topography, especially to soil texture, rainfall, vegetation cover, weathering, armoring can be mentioned as the major contributing factors. So we have to determine a number of associated parameters when running these simulations. I'm specifically talking about Siberia model today. For Siberia model, the only direct input dataset is a DEM. But if you go back to the erosion equation, which is here, we have to define beta 1, M1, N1, and D. So influence of the factors such as rainfall, soil texture, vegetation are all embedded in these parameters. So this parameterization or calibration is the key factor in landform evolution model improvement, and obviously the most difficult part. So we usually go to field to take soil samples, analyze for particle size distribution. So the photo here shows some field sampling, and then the hydrometer analysis we do. Then we have a flume, which is shown in this photo. Here we can place the sample along the flume and create artificial rainfall and measure the fluvial erosion by changing the flume angles. So this photo here shows the flume at 35-degree angle before, this one before running the water, and this is after running the water. So can you see the erosion at this photo on the right side compared to this one? You can see this kind of rills formed, some erosion. With all this data, using calibration curves, sometimes with our personal experience, I'm working with Professor Greg Hancock, who got 30 years of experience in this work. So with his input and using sensitivity analysis, we define the values for these parameters for each site separately to run the models. These photos at right shows some samples we have taken from a mine at 4 locations. And can you see the gullies in these photos? And look at these samples. These from one mine site, but 4 different locations. Look how different they are. The texture of soil, color, because all these piles are from different material. So this is why the site-specific parameters are really important. And the accuracy of the simulations of the models are based on correct calibration of the model with correct parameters. So look at these 2 plots. These are some examples of Siberia model outputs. We can run Siberia for any number of years and with different time steps, and can have DEM outputs, digital elevation model outputs, at desired years. For example, I can run Siberia for 100 years with 1-year time steps, which means at each year, the DEM is recomputed. So the erosion deposition is calculated, and this modified DEM is used for the next year and for the next time step, and so on, dynamically. So we get Siberia output file after running it, a text file, which shows a mean elevation at each time step. This can be used to calculate the erosion rates and plot the erosion rates over the time. But we don't really need physical digital elevation outputs at each year for 100 years. That's 100 digital elevation models. Just assume like very high resolution 100 digital elevation models. We don't need to store that. It's too large. So you might need DEM outputs only for selected years. For instance, assume I need DEM outputs after 5 years, 10 years, 20 years, 50 years, and 100 years. So we can tell Siberia model to output DEMs at those years to visually examine them. So Siberia, this model is good for modeling long-term erosion and deposition. We can run this for hundreds or thousands of years. At each time step, as I mentioned before, the DEM is evolved, and this modified DEM is used dynamically for the next time step in simulations. The two plots here show a tailing pile using armoring parameters. The top one is after 100 years, after running Siberia simulations, and the bottom one is after 1,000 years. Can you see how gullies are propagated and the landscape is eroded after 1,000 years compared to 100 years? And this one is a plot from one of our current projects. Let me take a step back here. Many people believe building contour banks on slopes can reduce erosion. Of course, it has a logic and a widely accepted fact, but there's another opinion of believing contour banks can sometimes, remember not always, but sometimes at some locations can increase the soil erosion or would not make any significant impact. So we found this site, a mine rehabilitation site, which has two slopes, two adjacent hill slopes in two slightly different slope directions. Can you see it in this figure on left? The left half here, and the right half of the slopes are facing slightly different directions. But both these slopes, the left half and right half, show similar soil and vegetation characteristics covered by grass of similar vegetation density. Now, can you see on the left slope, we have contour banks, but in the right slope, we don't have those contour banks. So this is a really good study site to see what will happen to these contour banks after 100 years. So we ran Siberia for 100 years. The top figure here is after running Siberia for 100 years. This is the digital elevation model, the terrain after 100 years. And this figure at bottom shows the total erosion and deposition after 100 years. Red is erosion here, and blue is deposition. Can you see what has happened? So the erosion at contour banks are quite high. And what happened after 100 years? So the contour banks were all eroded or disappeared. Look at this one. You don't see any contour banks now. Both sides of the slopes are quite similar. So when we went to the field, we could physically observe that's happening as what we see in this model. So contour banks did not help in this landscape, but it might work in another landscape. So this is an interesting finding which supports the fact that in some areas, due to site-specific characteristics, contour banks are not effective. So finding this through Siberia model is quite interesting. There are many interesting findings, but we don't have time to go through all of them. Now I'll move to the last part of today's talk. So all these projects needed high-quality spatial data. In some cases, we created our own data, not only for this landform evolution models, but for all of my other projects. But many times we obtained freely available data sets. Sometimes they are available freely with public access. Sometimes we have to contact the data provider and access the data freely. I worked in Sri Lanka for many years as a lecturer at the University of Molatua and a researcher at the Artsy Clarke Institute. I found lack of available data sets as the main problem for spatial data-based research in Sri Lanka. In Sri Lanka and government institutions, often data sets are with persons instead of having them in a system. So when that person is moved or retired, the whereabouts of the data sets are unknown. But in the world these days, there's a big voice that the data sets developed by the government authorities should be publicly available. The argument is those were developed using the taxpayers' money, so they should be available for the general public. And research should be published in open access journal for the same reason. Obviously, there are some confidential data sets. Sometimes the authorities have to specifically process the data sets to provide what you want. So in such cases, there might be some costs involved, which is reasonable. But I believe many data sets in Sri Lanka should be publicly available on digital platforms with access for the general public, and especially for researchers. And especially it should be in a system, not with a person. So in the world, there are a lot of data sharing platforms, data repositories, data visualization platforms. This slide shows NASA's data visualization platform, WorldView. There you can find many global scale useful data sets. Look how many spatial data sets they are having. They categorize them based on application, air quality, ash plumes, drought, dust storms, fires, flood, and so on. You can download them freely and you can use for your research because it has a global coverage. You can have data for Sri Lanka from these platforms. In Australia, we have a similar platform from Geoscience Australia called Digital Earth, where we can visualize many useful national scale data sets. India also have such a data visualization and sharing platform called Bhuvan. And you know, NASA, ESA, the European Space Agency, JAXA from Japan, they all have shared many global scale satellite data sets publicly with free access. In Australia, if we go to data.gov.au website, we can search for thousands of spatial data sets. It's a hub for data sets. We really need such data hub and national data repository in Sri Lanka. That will help researchers and also the general public. But not only for researchers, such spatial data, as I told you, such spatial data sets are useful for the general public. For example, this is a screenshot from the website of the Newcastle City Council. Here they have added an interactive flood risk map in their website. If you are buying a property, you can check for flood risk, bushfire risk, mine subsidence, school catchment on interactive maps. So probably quite simple thing to do, very simple, basic example, but very effective way of providing useful spatial information for the general public. Why can't we do it? We got a lot of IT experts. It's a simple thing for them to do. So to conclude, I want to highlight 3 messages. Some remote sensing professionals think the spatial data they receive as perfect, God-given information. But remember, always the data has uncertainties. You should be aware of these uncertainties when working with spatial data. Then a popular quote, all models are wrong. This means always the models have uncertainties, but many of them are useful. That's just it's not just all models are wrong, but some are useful. So many of them are useful with a certain or reasonable accuracy level. Same with the landform evolution models. For example, like in Australia, they predicted this year to be a dry year in New South Wales, but this was one of the wettest years. So sometimes models work, sometimes there are uncertainties, unforeseen factors, so they can go wrong. And the next thing is many remote sensing professionals stick with the computers, never go out and believe data and results given by the satellite or someone else as perfect God-given ones. you have to go to the field when possible. I'm talking to the students now, mainly. I'm being a lecturer now, a teacher more than the presenter, because I see a lot of undergraduate students in the audience. So you have to go to the field when possible to see what's actually happening. So this avoids many misinterpretations. So another quote I like most is that correlation is not always the causation. I see many people relate two entities which are correlated statistically, so they end up with ridiculous conclusions. For example, this is out of spatial data. We know on hot summer days in Australia, ice cream sales go high at an outlet near beach. Also, during the hot summer days, more people get sunburns at the beach. So if you plot ice cream sales against sunburns, you might see a high correlation. So, but does this imply eating ice creams cause sunburns? So correlation is not the causation at this instance. So understanding this is very important in spatial data analysis, spatial data science, and overall in research. With that, I conclude today's talk. I added my Google Scholar profile here. If you wish to read more about different spatial data applications, initially I was planning to talk about 4 applications: landform evolution models, mineral exploration, wetland inundation mapping, and remote sensing of soil moisture. But I thought that'd be too long for this lecture, so I cut down to 2, and again I cut down to 1. So I ended up with one application, which I think is very suitable for today's audience. And link to the Siberia user manual is here. The reference for Siberia user manual. If you search for this, you can download it. Even Siberia is available for free downloading. And thanks again to Geological Society of Sri Lanka for inviting me to deliver this public lecture. It's an honor, and I wish you all good luck with your future endeavors. Thank you.
Thank you very much, Dr. Indishe Senanayake, for that fascinating and insightful presentation. And I'm sure our audience has gained a lot from your expertise. Now we'll move on to the Q&A session. For those who would like to ask questions directly, please feel free to unmute yourself and ask the questions. And then I'll read the questions in the chat box aloud for Dr. Senanayake to address. So any questions from the audience?
I don't mind if you ask questions in even Sinhala. Unfortunately, I can't speak Tamil, but I can answer any question in Sinhala even.
So any questions from the audience? In the chat box, we have a few questions, Dr. Indishe. So first question is that how can spatial data from multiple sources, for example, satellite imagery, drones, sensors, field surveys, be integrated to provide a comprehensive view of natural resource distribution? I will repeat again.
Please do so.
How can spatial data from multiple sources, for example, satellite imagery, drones, sensors, and field surveys, be integrated to provide a comprehensive view of natural resource distribution?
Yeah, that's a very good question. Like in most cases, satellite images alone or drone images alone or field data alone can't provide a comprehensive view of any application, any natural resource distribution or any application. So, for example, I just give an example of what we have done or what I've explained with landform evolution models. Here we use digital elevation models. That's through the LiDAR surveys, airborne LiDAR surveys. And for this, we need vegetation information. That we usually take from optical satellites using NDVI calculations. And then sometimes we have to go to field and not get the samples. Those are field data, and analyze them for particle size distribution. Put them together, then only we can get the clear picture. So it's always integration of all these the data sets together, and that's why GIS is important, because all this data, when they are spatial data, they have geographical referencing, so you can overlay them together. So that's the beauty of GIS, whether it's field data, whether it's remote sensing data, whether it's from drones, sensors, we can all them together with on a GIS platform. So always, or at least in most of the applications, we have to integrate them together to get a better picture.
Okay, we have another question. How can machine learning and AI techniques be used to predict changes in natural resource availability based on spatial data trends?
That's again a good question. Like people are using AI these days for most of the applications and machine learning. Look, I first put another application on mineral prospect 3D mapping in this lecture, but I first later I removed it to shorten the lecture. Now, machine learning is really good because we can find the complex, complicated relationships and come up with some useful solutions. But in some cases, very simple, straightforward methods work better. So if you go to my Google Scholar profile, if you look at the mineral prospect 3D mapping paper we published recently, we use very simple method, obviously with machine learning inside, but some other people have used more complicated methods to get the same result and spend months for that. But within a short period of time, we got the same results with a straightforward method. So the first thing, machine learning is really applicable once you have a lot of input data sets, output data sets. But what I want to say is you shouldn't blindly use it. In most cases, machine learning models are black boxes. We can't physically explain what's happening inside. So that's one of the issues with machine learning. I see many people are like paper mills, like they publish a lot of papers, like they have a lot of input data sets and output data sets for the machine learning model, publish a paper. But again, my last slide, correlation is not always the causation. So that comes up like, how can you explain the causation in certain cases? So there are two sides of machine learning. If that is used with a proper understanding, that's good. But if you use machine learning blindly, that's always questionable.
Thank you. So the next question is that what role does IoT, that means Internet of Things, play in real-time spatial data collection for natural resource monitoring and management? Shall I repeat it?
Yeah, please do so. Yeah.
What roles does IoT, that means the Internet of Things, play in real-time spatial data collection for natural resource monitoring and management?
Yeah, like real-time data collection is not like, it always depends on the application. Sometimes for some of the applications, you really need real-time data. So today with the WebGIS, we have a lot of facilities for real-time data collection. And one of the interesting things what I want to say is we can use real-time data collection with integrated with we call this as what is called the term is the social. I can't get the term exactly, but we can involve people, students, and general public for data collection. Like in many cases, we developed mobile apps to collect real-time data. Once people collect the data, they can real-time upload into a data portal, and that can be analyzed in a different platform. So citizen science in citizen science projects, real-time data collections are really important. So there are a lot of applications in that field.
There are two more questions, sir.
Yeah.
What are the emerging trends and innovations in spatial data science?
Yeah, that's a really good question, and a question which is really difficult to answer because this technology is evolving every day with the new data sets, new algorithms, AI. Every day it's different. So every day what we get is different. We can't sometimes catch up with what's going on. It's because it's really fast moving field. So the answer to that question is it depends on your field again, like what application you are using. So it depends on that. It can be algorithms, it can be models, it can be AI, it can be data. But for students, it's really important to learn supportive skills for future, I guess. Like it's not just learning a GIS software, but I think that the base of that question is what they want to learn for the future. But the supportive skills like AI, machine learning, programming, those things are really important. Just GIS software alone won't do the magic.
Yeah, thank you, sir. So the next question is that what is the difference between the digital terrain model and DEM?
Yeah, okay. Digital terrain model is the terrain, the ground points. If you take ground is digital terrain model, but some people take like what is on the surface. It can be trees or it can be buildings. So the surface elevation is with all these buildings and all these structures is digital elevation model, and digital terrain model is just the ground points without buildings or trees. But in general, like people use the term digital elevation model or DEM for the terrain. That's the difference.
One last question, sir. How can we use DEM to predict natural hazards?
That's really a good question. Like we use DEMs for, like, for example, this mine rehabilitation. We use this kind of DEMs. That's one application. But and then for landslides, we use it's similar. We use digital elevation models, and also in the mining industry, we not only use digital elevation models, but we take photogrammetric mine surfaces, which we use for rockfall modeling. We have done some work with rockfall modeling. We've done a work, for example, based on digital elevation model and vegetation. We modeled the erosion, and we can always apply. What happened if you had more vegetation? Will this slope stable? What happened if we change the particle size distribution? If we add more different topsoil, will this be stable? What happened if we design it in a different way? The pile of the waste pile in a different way, would that be stable? So not only natural hazards, but man-made hazards, we can use digital elevation model.
Thank you, sir. One more question. Is GeoPanda superior to the conventional GIS softwares like QGIS and ArcGIS?
I don't know. The answer is I don't know. But what I use these days is mostly some coding, like for example, because when you're working with rasters, I see raster as a matrix with numbers. So when you have a matrix with numbers, you can process it in MATLAB or Python rather than using a GIS specific software. So I don't know really what the answer for that question. Each software has their own pros and cons. For example, many people don't like ArcGIS because it's a commercial software, too heavy, but sometimes it works well compared to some other software. I don't really know. I can't answer that question really.
Okay, with that, I concluded all the questions in the chat box. So are there any questions from the audience? You can unmute and directly ask from the Dr. Indishe.
I'll just add something to the last question. Another thing, like we have a lot of big data these days. and we need a lot of storage capacity. We need a lot of storage capacities. So people are moving to cloud-based solutions. For example, the Google Earth Engine. Not on Google Earth Engine is global, but we have a similar platform in Australia, Digital Earth Australia Sandbox. So in those platforms, we have data repositories. We can import data, analyze them using virtual computer powers, cloud-based computing. So we don't have to download any data sets in our computer, or we don't analyze the data sets in our computer. We can use the Google's computer power for our processing power for our applications. So that's one of the things I want to highlight.
Yeah. One last question, sir. Are machine learning models reliable to detect anomalies to reveal natural resources?
If the data sets are good, if the algorithm is good, yes, there's a possibility. But the thing is, like, again, we should be able to explain why it happens. Like, again, if I go take a step back, Professor Gary Vilgus, the developer of Siberia model, he was always telling, I will ask the question why. Until you give an answer, I will keep asking why. So, see, machine learning models, the problem is sometimes you don't have an answer for why it happens in that way if it is a black box. If it is a multilinear regression or a model which we can still machine learning, but model we can explain a meaningful model. We can explain what's the what physically happening. But if some AI models are like black boxes, we just put some input data and target data, we get an output. We don't know what's happening inside. So can we really explain what is happening there? And can we exactly tell that its correlation is the causation? So if the data is good, and if the data is meaningful, if the model is meaningful, reasonable, then you'll get very good results. Machine learning is so powerful. I'm not denying machine learning is powerful. Machine learning is really powerful technique, but you have to use it with caution. That's what I'm saying.
Okay, thank you, sir. So thank you all for your
You're welcome.
thank you all for your engaging questions and for being such a attentive audience. And special thanks goes to Dr. Indishe Senanayake for sharing his valuable insights with us today. Your lecture has given us a deep understanding of how spatial data science can revolutionize the natural resource management, especially in the context of Sri Lanka. So I also like to thank the Executive Committee of GSSL for organizing this event, and to everyone behind the scenes who helped make it success. And thank you, sir, once again.
Yes, thank you very much.
I think, so one of my teachers, the things that I have learned from you at University of Morocco is very, very supportive for me to progress in my research studies as well. And finally, once again, thank you for joining us. And we hope to see you at our future events, and have a great day. Thank you very much, sir.
Thank you very much.